Hi, welcome back to Easy Maths with Dr. Nasir, your path to maths confidence. Don't forget to share, like, and subscribe so you never miss a conceptual concrete lesson. Well, now we will see some more exercises related to first order linear ODEs. Well, see an exercise. Find the general solution of the ODE dy by dx plus 2xy is equal to x cubed, where x belongs to R. Determine whether there is any transitive term in the general solution. We'll see solution. Comparing the ODE 1.1 with standard form, we have p of x is equal to 2x, where x belongs to R. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of 2x dx. So we have mu x is equal to exponential of s square, where x belongs to R. Multiplying the ODE 1.1 by the integrating factor, we have exponential s square dy by dx plus 2x exponential s square y is equal to s cube exponential s square, where x belongs to R. So we have d by dx of exponential s square y is equal to s cube exponential s square, where x belongs to R. So we have d of exponential s square y is equal to s cube exponential s square dx, where x belongs to R. Just taking integral, we have integral of d of exponential s square y is equal to integral of s cube exponential s square dx plus c, where s belongs to R and c is arbitrary constant. So we have exponential s square y is equal to integral of s cube exponential s square dx plus c, where s belongs to R and c is arbitrary constant. Now we consider alpha of x is equal to integral of s cube exponential s square dx. To solve this integral, just substitute u is equal to s square, so du is 2x dx. So alpha of x is equal to integral of u exponential u du by 2. Just integrating this by parts, we have 1 by 2 is outside u as it is, integral of exponential u du minus integral of exponential u du, derivative of u is just 1 du. So we have 1 by 2 u exponential u minus 1 by 2 exponential u. Just taking exponential u common, so we have 1 by 2 into u minus 1 exponential u. Now u is equal to x squared, so we have alpha of x is equal to 1 by 2 x squared minus 1 exponential s squared. So exponential s squared y is equal to 1 by 2 x squared minus 1 exponential s squared plus c, where x belongs to R and c is arbitrary constant. Just dividing this by exponential s squared, we have y of x is equal to 1 by 2 x squared minus 1 plus c exponential of minus s squared, where x belongs to R, c is arbitrary constant, which is the required general solution and contains the transitive term exponential of minus s squared. We'll see another exercise. Find the general solution of the ODE x squared dy by dx plus xy is equal to 1, where x belongs to R other than 0. Determine whether there is any transitive term in the general solution. We'll see solution. The given ODE 1 by 2 can be expressed as dy by dx plus 1 over xy is equal to 1 over s square, where x belongs to R other than 0. Comparing ODE 1 by 3 with standard form, we have p of x is equal to 1 by x, where x belongs to R other than 0. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of 1 over s dx, which is equal to exponential of log of x absolute. So mu of x is equal to x absolute, where x belongs to R other than 0. Multiplying the ODE 1 by 3 by the integrating factor, we have x absolute dy by dx plus x absolute over x into y is equal to x absolute over s square, where x belongs to R other than 0. Now for x belongs to minus infinity to 0 open interval, we have x absolute is equal to minus x. Therefore from equation 1.4 we have minus x dy by dx minus x over x into y is equal to minus x over x square, where x belongs to minus infinity to 0 open interval. So we have minus x dy by dx minus y is equal to minus 1 over x, where x belongs to minus infinity to 0 open interval. Multiplying this equation by minus 1, we have x divided by dx plus y is equal to 1 by x, where x belongs to minus infinity to 0 open interval. Well, this can be expressed as d by dx of xy is equal to 1 by x, where x belongs to minus infinity to 0 open interval. So we have d of xy is equal to 1 by x dx, where x belongs to minus infinity to 0 open interval. Just taking integral, we have integral of d of xy is equal to integral of 1 by x dx plus c, where x belongs to minus infinity to 0 open interval and c is the arbitrary constant. So we have xy is equal to log of minus x plus c, where x belongs to minus infinity to 0 open interval and c is the arbitrary constant. So y of x is equal to log of minus x plus c over x, where x belongs to minus infinity to 0 open interval. So y of x is equal to log of x absolute plus c over x, where x belongs to minus infinity to 0 open interval and c is the arbitrary constant. Now we consider x belongs to 0 to plus infinity open interval. For this, x absolute is equal to x. Therefore, from equation 1.4 we have x divided by dx plus x over xy is equal to x over x square, where x belongs to 0 to plus infinity open interval. So we have x divided by dx plus y is equal to 1 over x, where x belongs to 0 to plus infinity open interval. So d by dx of xy is equal to 1 over x, where x belongs to 0 to plus infinity open interval. Well, this can be expressed as d of xy is equal to 1 by x dx, where x belongs to 0 to plus infinity open interval. Just taking integral, we have integral of d of xy is equal to integral of 1 by x dx plus c, where x belongs to 0 to plus infinity open interval and c is the arbitrary constant. So we have xy is equal to log x plus c, where x belongs to 0 to plus infinity open interval and c is the arbitrary constant. So xy is equal to log of x absolute plus c, where x belongs to 0 to plus infinity open interval and c is the arbitrary constant. So y of x is equal to log x absolute plus c over x, where x belongs to 0 to plus infinity open interval and c is the arbitrary constant. Thus, from equations 1.5 and 1.6 we have y of x is equal to log x absolute plus c over x, where x belongs to r other than 0 and c is arbitrary constant, which is a required general solution and contains the transient term 1 by x. Well, see another exercise. Find the general solution of the ODE divided by dx is equal to 2y plus s square plus 5, where x belongs to r. Determine whether there is any transient term in the general solution. Well, see solution. The given ODE 1.7 can be expressed as dy by dx minus 2y is equal to s square plus 5, where x belongs to r. Comparing the ODE 1.8 with standard form, we have p of x is equal to minus 2, where x belongs to r. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of minus 2 dx. So we have mu x is equal to exponential of minus 2x, where x belongs to r. Multiplying equation 1.8 by the integrating factor, we have exponential of minus 2x divided by dx minus 2 exponential of minus 2x, y is equal to s square exponential of minus 2x plus 5 exponential of minus 2x, where x belongs to r. So we have d by dx of exponential of minus 2x y is equal to s square exponential of minus 2x plus 5 exponential of minus 2x, where x belongs to r. Well, this can be expressed as d of exponential of minus 2xy is equal to x square exponential of minus 2x plus 5 exponential of minus 2x dx, where x belongs to r. Just taking integral, we have integral of d of exponential of minus 2xy is equal to integral of x square exponential of minus 2x plus 5 exponential of minus 2x dx plus c, where x belongs to r and c is the arbitrary constant. So we have exponential of minus 2xy is equal to integral of x square exponential minus 2x dx plus 5 integral of exponential minus 2x dx plus c, where x belongs to r and c is the arbitrary constant. So we have integral of x square exponential minus 2x dx minus 5 by 2 exponential minus 2x plus c, where x belongs to r and c is the arbitrary constant. So we have x square exponential minus 2x over minus 2 minus integral of 2x exponential minus 2x by minus 2 dx minus 5 by 2 exponential minus 2x plus c, where x belongs to r and c is the arbitrary constant. Well, this can be expressed as minus 1 by 2 x square exponential minus 2x plus integral of x exponential minus 2x dx minus 5 by 2 exponential minus 2x plus c, where exponent to r and c is arbitrary constant. So we have minus 1 by 2 x square exponential minus 2x plus x exponential minus 2x over minus 2 minus integral of exponential minus 2x over minus 2 into 1 dx minus 5 by 2 exponential minus 2x plus c, where exponent to r and c is arbitrary constant. So we have minus 1 by 2 x square exponential minus 2x minus 1 by 2 x exponential minus 2x plus 1 by 2 integral of exponential minus 2x dx minus 5 by 2 exponential minus 2x plus c, where exponent to r and c is arbitrary constant. So we have minus 1 by 2 x square exponential minus 2x minus 1 by 2 x exponential minus 2x plus 1 by 2 exponential minus 2x over minus 2 minus 5 by 2 exponential minus 2x plus c, where exponent to r, c is arbitrary constant. So exponential minus 2x y is equal to minus 1 by 2 x square exponential minus 2x minus 1 by 2 x exponential minus 2x minus 1 by 4 exponential minus 2x minus 5 by 2 exponential minus 2x plus c, where exponent to r and c is arbitrary constant. Just simplifying, we have exponential minus 2xy is equal to minus 1 by 2 x square exponential minus 2x minus 1 by 2 x exponential minus 2x minus 11 by 4 exponential minus 2x plus c, where exponent to r, c is arbitrary constant. Just multiplying this by exponential of 2x, we have y of x is equal to minus 1 by 2 x square minus 1 by 2 x minus 11 by 4 plus c exponential of 2x, where exponent to r and c is arbitrary constant, which is a required general solution and does not contain any transitive term. Well, see another exercise. Find the general solution of the ODE x dy by dx minus y is equal to x square sine x, where exponent to r other than 0. Determine whether there is any transitive term in the general solution. Well, see solution. The given ODE 1.9 can be expressed as dy by dx minus 1 by x y is equal to x sine x, where exponent to r other than 0. Comparing the ODE 1.10 with the standard form, we have p of x is equal to minus 1 by x exponent to r other than 0. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of minus 1 by x dx, which is equal to exponential minus log of x absolute, which is equal to exponential log of x exponent minus 1. So we have mu of x is equal to x absolute exponent minus 1. So mu of x is equal to 1 over x absolute, where exponent to r other than 0. Multiplying equation 1 by 10 by the integrating factor, we have 1 over x absolute dy by dx minus 1 by x into x absolute into y is equal to x over x absolute sine x, where exponent to r other than 0. Now for x belong to minus infinity to 0 open interval, we have x absolute is equal to minus x. Therefore from equation 1.11 we have 1 over minus x dy by dx minus 1 over x into minus x y is equal to x over minus x sine x, where exponent to minus infinity to 0 open interval. So we have minus 1 by x dy by dx plus 1 over x square y is equal to minus sine x, where exponent to minus infinity to 0 open interval. So we have 1 by x dy by dx minus 1 by x square y is equal to sine x, where exponent to minus infinity to 0 open interval. So d by dx of y by x is equal to sine x, where exponent to minus infinity to 0 open interval. So we have d of y by x is equal to sine x dx, where exponent to minus infinity to 0 open interval. Just taking integral, we have integral of d of y by x is equal to integral of sine x dx plus c, where exponent to minus infinity to 0 open interval, and c is arbitrary constant. So y by x is equal to minus cosine x plus c, where exponent to minus infinity to 0 open interval, and c is arbitrary constant. So y of x is equal to x minus cosine x plus c, where exponent to minus infinity to 0 open interval, and c is arbitrary constant. Now we consider x belong to 0 to plus infinity open interval. For this, x absolute is x. Therefore from equation 1.11 we have 1 by x dy by dx minus 1 by x square y is equal to x by x sine x, where exponent to 0 to plus infinity open interval. So we have 1 by x divided by dx minus 1 by x square y is equal to sin x, where x belongs to 0 to plus infinity open interval. So we have d by dx of y by x is equal to sin x, where x belongs to 0 to plus infinity open interval. So d of y by x is equal to sin x dx, where x belongs to 0 to plus infinity open interval. Just taking integral, we have integral of d of y by x is equal to integral of sin x dx plus c, where x belongs to 0 to plus infinity open interval and c is arbitrary constant. So we have y by x is equal to minus cosine x plus c, where x belongs to 0 to plus infinity open interval and c is arbitrary constant. So y of x is equal to x into minus cosine x plus c, where x belongs to 0 to plus infinity open interval and c is arbitrary constant. Thus from equations 1.12 and 1 by 13 we have y of x is equal to x into minus cosine x plus c, where x belongs to r other than 0 and c is arbitrary constant, which is the required general solution and it does not contain any transitive term. We'll see another exercise. Find the general solution of the ODE x divided by dx plus 2y is equal to 3, where x belongs to r other than 0. Determine whether there is any transitive term in the general solution. We'll see solution. The given ODE 1.14 can be expressed as dy by dx plus 2 by xy is equal to 3 by x, where x belongs to r other than 0. Comparing the ODE 1.14 with standard form, we have p of x is equal to 2 by x, where x belongs to r other than 0. So integrating factor is mu of x is equal to exponential of integral of px dx, which is equal to exponential of integral of 2 by x dx, which is equal to exponential of 2 log of x absolute. So we have exponential log of x absolute square. So we have x absolute square. So mu of x is equal to x square, where x belongs to r other than 0. Multiplying equation 1.15 by the integrating factor, we have x square divided by dx plus 2xy is equal to 3x, where x belongs to r other than 0. So d by dx of x square y is equal to 3x, where x belongs to r other than 0. So d of x square y is equal to 3x dx, where x belongs to r other than 0. Just taking integral, we have integral of d of x square y is equal to integral of 3x dx plus c, where x belongs to r other than 0 and c is arbitrary constant. So x square y is equal to 3 by 2 x square plus c, where x belongs to r other than 0 and c is arbitrary constant. So y of x is equal to 3 by 2 plus c by x square, where x belongs to r other than 0 and c is arbitrary constant, which is the required general solution and contains transitive term 1 by x square. That's it for today. Well, in the next lecture, we will see some more exercises. Don't forget to share, like, and subscribe. Easy Math with Dr. Nasir, so you never miss a conceptual concrete lesson.